Hello, students. Greetings to all, and I welcome you all for this AICTE Paragraph Gate Training Program. And today we are going to see the subject on computer networks, the topic on distance vector routing algorithm. I'm glad you're all eager to learn about this topic, distance vector routing algorithm, and I'm sure that we are going to see some gate questions that is relevant to this particular topic, and we are going to try to solve all these topics. Thank you all for joining. And now let me go to the class. So as of previously, we have discussed something about the data link layer. In the previous classes, we studied something about the data link layer and what are the functionalities in data link layer. And now we are going to study the topic on network layer. This is the third layer of the OSI. It's something what is called to be as the network layer, as we all know, and we are going to study something about the functionalities that is there in network layer. So let me go to the topic. So today we are going to use some of the routing algorithm. One of the routing algorithm is a distance vector routing algorithm. So before going on to see something about the distance vector routing algorithm, and now let me study something about, or let me know something about what actually the network layer is, just an giving some idea about what is a network layer. Okay. So network layer, as I said, it's the third layer. So the main role of this network layer is to transfer the packets from source to destination. Source can be at one end and destination can be at another. It doesn't mind about where the source and where the destination is, but its main role to transfer the data between the source and destination. That is the main responsibility and functionality of network layer. And for this, for transferring of data packet between the source and destination, what this layer is going to do, how it is going to find where the destination is, and how it is going to transfer the data. Because we don't know where our system is. It can be of any remote place, but your system, your network, is going to find it out and it is going to deliver that packet to the intended recipient. How this could be possible? So that is what we are going to study. That magic, that's something that deals with something about this network layer. Okay. So as I said, this network layer, it is involved transferring the packet between the source and destinations. And for this transmission of data packets, we have various other connecting devices that helps in this transmission of data packets. We all know that. Okay, the main important one of the connected device is something about what we call to be as router. We all know what is router. Okay, it takes a major role in transferring this data packet between the source and destination. Okay, so distance vector. So the topic on distance vector routing algorithm. Okay, so as I said, the node of a network layer, okay, it's going to transmit the packet or transport the segment from sending to receiving host. Okay, so what it is going to, so it is going to transfer the packet. Okay, what it has to do. So what the network layer is going to do at the sender side. At the sender side, the network layer takes the responsibility of encapsulating the packet or the segment, what it is a packet or we call a segment. Okay. So here it is going to encapsulate the packet into a datagram packet, okay, and delivers that packet to the next layer, that is the data link layer. And after that, it at the receiver side, what happens in the sense that packet, it is going to receive that packet from the data link layer, the data segment, and it is going to decapsulate that packet and transmit the packet to the higher layer. Okay, that is the transport layer. Okay, this is the what your network layer is responsibility. So this is what it is going to do in between. Okay, so network layer, it receives the packet from the at the sender side from the upper layer, that is your transport layer. Okay, and it is going to encapsulate the data packet and send the packet to the data link layer for the further transmission of data packet from the source to destination. And at the destination side, what network layer is going to do in the sense, it's going to receive the packet from the data link layer. It is going to decapsulate the packet not to get the data, and then it is going to transfer that data packet to the upper layer, that is the transport layer. and next feature it goes on. So this is the role of this network layer. Okay. So here, the source and destination aside, all the 5 layers of TCP, all the 5 layers of TCP it works place. Whereas the intermediate nodes, that is the intermediate nodes between the source and destination, it works only on with the next 3 layers. Okay, the routing part takes place here. Okay, it's because that is why it deals only with the 3 layer. That is the network data link and the physical data link and the network. Okay, it deals that only for routing of the data packets. Okay, so just they need to whereas the higher layer like the transport layer or the application layer, that layers have been used only for the controlling purpose. That is the intermediate nodes. It uses only 3 layers, but it can uses the higher layer only for controlling purposes. But this 3 layers is quite enough for the intermediate nodes. Whereas the source and destination, it needs all these 5 layers in the TCP for sending and receiving the entire data packets. Okay. So next, very important thing, what we have to know, what we have to do is what is the responsibility or the functionality of the network layer? This is a two key network layer function. But there is a primary function. What about this network layer? We have to know the primary function of this network layer. So talking about this primary function is nothing with the packetizing. Okay, packetizing is the primary function where it has to encapsulate and decapsulate the data packet that is being received by the upper layer as well as from the lower layer. Okay, that is the main functionality of network layer. And afterwards, for transmitting the data packet from source to the destination, it needs another 2 important key components. That is something what is called to be as the forwarding of the data packets, and another one something what is called to be as the routing of data packets. What is meant by the forwarding? Okay, so forwarding in the sense here it talks about the way the packet is delivered to the next station. Forwarding main responsibility of forwarding is the way it takes the way it has its responsibility for delivering the packet to the next stations. How, what, and what way it is delivering the packet. That is what the forwarding plays role. Okay, that is moving the packet from router's input to appropriate router output. That is how the way it is going to deliver the packet to the next station. Okay, that's routing. What is this routing? It is the way the routing table, because we all know that as I said, the network layer, it for this transmission of data packets between the source and destination, it needs various connecting devices, and of course, one of the important is router. Okay, we all know that each and every router has its own routing table for getting the income packet at the incoming side and then delivering the packet at the output. Okay, for maintaining that, it has its own routing table to be maintained. Okay, so this routing, what is this routing here? The second key point that is routing. So what it deals with the way the routing table are created and helps in forwarding the data packet. We all know that forwarding is the way the packet is moved to the next station, because it has to deal with each and every step how a packet is moved from one node to another node. Okay, so the way the packet is forwarded is built with something of forwarding, and routing is it has to know the way the routing table have to be created that helps in forwarding the data packet. So it determines the route taken by the packets from the source to destination. So how the route? What is the route? In what way we can able to transfer the data packet? What is the shortest path route in order to reach my destination? In what is the easiest route so that the packet can be transferred without any conjunction or collision happens? Okay. So that is something about the routing techniques. These are the 2 important components of network layer function. One is the forwarding, another one is the routing. As I said, forwarding is is the way it delivers the packet to the next station, and routing is the way it maintains the routing table that helps in forwarding of the data packets. Okay, these are the 2 important functionalities of network layer. So next we're talking about as I said, the role of routing, routers. So routers, the main role of this routers is it is the one which is going to provide the way or the route for transferring the packet. Okay, so that is the main role of route. It is the one which is going to deliver you the route for transferring the packet between the source and destination. That is the main role of router by maintaining something what is called as routing table. Okay, so this is something what is called to be as the routing table, and each routing table is maintained by the routing algorithms. Algorithms plays a vital role in network layer for maintaining this routing algorithm, because this routing algorithm maintaining this routing table. Okay, because the routing table is the important part, because that is what the key component for each and every router for sending the packet in a right destination, the right path. Choosing the right path is the main important functionality of the router. So which particular path this particular packet has to be sent, which particular port this particular packet has to be sent, which particular output this particular have to be sent. And that is dealt only with the help of this routing table. The routing table plays a vital role. Okay, so the maintaining and updating of this routing table is done by something what is called to be as the routing algorithm. So that is the important concept. This is where we are here right now today. Routing algorithms. Routing algorithms plays a vital role of maintaining this routing table, because the routers are the important component in network layer for sending the packet and choosing the best route and finding the clear route for the packet to be sent from source to destination with the help of this routing table. So routing table is very important. Each and every router maintains a separate routing table that has to be that delivers the right path for the packet to be transmitted from one station to another station in order to reach the destination in the correct time. Okay, so this is something about the routing table. Okay. So this routing table, talking about, okay, let me see. This is the component of a routing. This is something about the routing table, what it has. Each and every routing table have some various incoming link as well as it have various outgoing link. Okay, so each and every incoming, so the packet can receive to this router with help of in various incoming link. So now all these packets has to be in a special queue, and that is what is called to be as a router buffer. The packets that is to be received by the router, it is been assembled in the routing buffer. Okay, the router buffer will assemble all the packets that is being received, and the packets will be processed, and it will process it in the sense now the router using the help of this routing table, it decide which particular packet, because each and every packet will have something what is called to be as the, because as we studied in the data link layer, each and every packet has a frame format where it deals with the source address as well as destination address. We all know that something about it. And network layer, we all know that each and every network layer, the special address that plays vital role is the IP address. Okay, with help of the IP address, the source IP address and destination IP address, router takes responsibility of which particular outgoing link the packet has to be sent. So that is to be processed by the router. Okay, with the help of the routing table. So this routing table have to be updated each and every time. Okay, so the routing table, the maintenance of this routing table is of two types. We talk about. Okay, so the routing table is maintained by something what is called a static routing. We can maintain by means of static routing table, as well as we can also maintain in the form of a dynamic. Okay, we're talking about this static in the sense the information that is stored in this routing table are entered manually. Okay, so it is not going to perform automatically. So with the manual entry, so its importance in the static routing table. If there is any change in the network, or if there is any link problem, or there is no route a bridge between, or there is no one of the routers in its path is not working, so that has to be updated manually by the in routing table. So this is something about what is called to be as static, whereas of course we have something what is called as dynamic, where each and every router will dynamically or automatically it will update its routing table, okay, without any interference from the manual part. Okay. Automatically the routing table will be updated. So that is the main role of this routers. Okay, routers automatically it will update its routing table in the case of any change in the topology of the network. So this is something about the routing table, the role of routers in the network layer for transmitting the packet from one end to another end. So as I said, each and every router has its own routing table, and that table has to be maintained with the help of the routing algorithms. So what are the different routing algorithms we have in a network layer is something what is called as distance vector routing algorithm, link state routing algorithm, border gateway routing algorithm, and routing information protocol routing algorithm. So, and OS open shortest path first OSPF. This is our another routing algorithm. We have several routing algorithms plays a vital role in network layer for updating of this routing thing. And now this is the routing algorithm, as I said. Okay, the main part of this is the important part of the network layer and is responsible for deciding on which output line to transmit an incoming packet. So that is the responsibility of this routing layer. So virtually, for example, if it is a virtual circuit in the sense, it is made only at the time of setup. When we set up our initializing system, so it is at that time the routing algorithm has to be set up. Okay, decision has to be taken. Okay, so there are various algorithm properties because, as I said, routing algorithm plays vital role in updating of this routing table. There are various algorithm properties like correctness, simplicity, robustness, stability, fairness, optimacy, and scalability. So these are the various uh, properties that algorithms have in order to maintain an update of the routing table. Okay. So next we're talking about now let me go to the first routing algorithm, the one the topic that we are going to see today, that is the distance vector routing algorithm. Okay. So we are going to see something about the distance vector routing algorithm now. Okay, so talking about this distance vector routing algorithm, this is one of the oldest routing algorithm as we see, we can say because it has been found earlier in the 1980s itself. Historically, it is known as old ARPANET routing algorithm. Okay, or we can also call that distance vector routing algorithm as Bellman-Ford routing algorithm. Because by using this Bellman-Ford equation only, we are going to solve the problem of updating the routing table. Okay, that is why we also have another name for this distance vector routing algorithm. It's because this is one of an important gateway name. What is the name for distance vector routing algorithm is Bellman-Ford algorithm. Okay, so this is another gateway we have here. Okay, this next, the basic idea. What is this actually? This distance vector, as I said, routing algorithm. What does this routing algorithm does? It is going to update the routing table. If there is any change in the network, the immediate change in the network will be updated periodically for every time second or any period of time or whatever it is. Okay, this routing table have to be updated with the help of this routing algorithm. And each and every different types of network, it uses different types of algorithm for updating its routing table based on the scenario, based on the place, based on the setup that a network is, whether it is a wired or wireless or Wi-Fi or whatever it is. So based on that, we have different types of routing algorithm that helps in updating the routing table because routing table plays a vital role for each and every router that's going to provide you the finest path for the foot to reach your destination. Okay. So now talking about the basic idea of this distance vector routing algorithm is that here each and every router is going to maintain, as I said, it's going to maintain a table something what is called to be as the distance vector table. And that what that table contains is contains the distance between itself, the distance or it has its own not reach its own node. Okay, distance between itself and also all possible destination nodes. Okay, so the topology of the nearest node. To have the root of all the nodes that is nearby. That is what they are saying. It's counting the distance between itself and all the possible destination. Okay. So that is what the distance vector table. So it is so each and every node is going to maintain a table, and that is what is called to be as the distance vector table that contains distance between itself as well as all the possible destination. Okay. So now, what is this distance? Okay, distance between itself and distance between node in the sense that we are talking about something about the distance. So this distance is based on various metrics. We can use various metrics in order to calculation of this distance. So on our computer, using the information based on the neighbor it have or the distance or the hop or based on the hop it have or number of hops it needs to not reach the destination or the delay time it have to reach the destination or the cost it takes not to reach the destination. These are different metrics it is used in order to that is to be updated in the table. Okay, so this distance vector table it have the distance within itself and all the possible destination node in the sense that distance it is of different metrics. Either it can be the hop count or either it can be the delay time in order to reach the respective node or it can be the cost it takes in order to reach the respective node. So these are the different metrics it uses in the distance vector table in order to update it. Okay. So talking about this distance vector routing algorithm, the main role of this distance vector routing algorithm is that, so what is it is going to give you the least cost route between two nodes in the route with minimum distance. So that is the important concept. Okay, what is the distance vector routing algorithm? What is this going to do? It is going to provide you the least cost route, the least cost, because here we are going to study something about cost metrics, and the node that have the least cost route path, that is going to be selected between the source and destination for the delivery of the data packets. As we all know, network layer responsibility is delivery of data packets between source and destination. So for selecting the path, it is going to choose one of the algorithm we are going to studying here is distance vector routing algorithm, and that algorithm, what metric it is going to use in order to choose the path between the source and the destination, is that path that is being chosen is nothing but it is the least cost route. Okay, so with the minimum distance. That is what we are going to see. And this distance vector routing algorithm is implemented in another protocol algorithm is, that is the routing information protocol, RIP. Okay, it is highly implemented in RIP. Okay, so talking about the next. So what is this distance vector routing algorithm? Okay, that is what we are going to study now. This distance vector routing algorithm is iterative, as well as it is asynchronous, as well as it is distributed. These are the three main characteristics of distance vector routing. It is iterative, asynchronous, as well as it is distributed. So distributed in a way, what do you the meaning of this distance vector routing algorithm? What is that does distributed in a way, in the sense that, because as we all know that each and every node has a distance vector table, that table has to be updated each and every time. Okay, so for that case, what it has to do in this end, it has to it is distributed in a way that it is distributed in that each node receives information from one or more of its directly attached neighbors, performs calculation, and then distributes the result back to its neighbor. So that is why we call that as distributed. So what does it mean here is that what the distance vector routing algorithm does here is, as I said, each and every node has distance vector table. So it is going to directly it lives with the nearby station. It is going to share its routing table with the nearby information, and it is going to get the information from the nearby table, and it's going to update based on the information of the nearby table. It is going to update its own. It is going to process and it's going to update by its own, because basically when a new station enters into a network, it doesn't know who are the nearby, and where is the other node, what is the next node and the nearby node. So it doesn't know. So it has to learn by sharing of data, by sharing of knowledge, of information of regarding the table it has. So what initially it has its only own information. So by sharing of information, and directly it mingles with the neighbor and get the information from the neighbor. Based on the information of the neighbor, it updates its own table, and gives that updated information to the neighbor. So that is the manner of distance vector routing algorithm, and that is something what is called to be as the distributed. So distance vector routing algorithm, one of the characteristics is distributed in the sense, as I said, it is going to, what it is going to do this, it is going to get directly get involved with its neighbor, get the information of this table, update its own, and then get and send its updated information directly to its neighbor. So that is where we this is distributed in a way. And iterative, what it means is iterative in the sense at how many times it iteratively it happens. Okay, this sharing of information, updating, and then setting the information, and then updating, getting the information, updating, it will go iteratively until it gets the idea of the entire topology it sets up in. Because when a new node set up to a new environment, it does not know what is the environment there. So until it learns about that environment, it continuously shares and get the information by sharing and getting the knowledge, and then that is why we say that it is iterative. Okay, so it doesn't stop. It will goes on iteratively. Okay, that is why that is one of the characteristics of this distance vector routing algorithm. And last one is something about the asynchronous. It does not need that each and every node has to be synchronized, really, in touch with this particular node. No, there's no need. It does not require that type of operation to be performed. It is asynchronous. It just share with its neighbor, get the information if it delivers. That's it. It is asynchronous. That is what the three important characteristics of this distance vector routing algorithm. At the same time, this distance vector algorithm is a dynamic algorithm. It changes at runtime. The topology changes. It is not static. It changes. Okay, and it is mainly used in ARPANET as well as I said, this distance vector routing is also implemented in another routing protocol, what is called routing information protocol or IP. As is each and every node in a distance, it has its own table known as something what is distance table, what is called as vector. Okay, it has a distance vector table. So that is what it's represented in the last point. Okay, so this is something about the distance vector routing algorithm. Next, when talking about this, what is this distance vector routing algorithm? As I said, each and every route information that is have in the kept by the distance vector router. So what is this distance vector router? The information what does it have here is here in this distance vector routing algorithm. Each router that is going to work on with the distance vector routing algorithm is a distance vector router. Okay, so here each and every router has its own ID because here each and every node that forward and routes the data is router. Okay, so here what is the in the sense each and every router here has its own ID. And at the same time, the what it is the router does is on the link it is being associated or connected to the router. Okay, it is connected with the means of either it can be a static or it can either be a dynamic, and it deals with only of the cost. The cost is nothing but the minimum distance it takes off for transmitting the packet. Minimum distance not to reach the nearby node. Okay, next hop node or whatever it is. Okay, so this is sort of kind of information it have. The DB router has it. That is, each router has its own ID as well as it's associated with each link that is connected to the router. Okay, so each and every link that is associated with, and therefore that ID is associated with each and every link, and therefore there is a link cost based upon the either it can be a static or it can either be a dynamic. So initially, as I said, no does not know anything. It is null. By sharing and getting the information and updating its table only, it started to know about who are all the nearby neighbors and about the entire topology. Okay, so at the very initial stage, it is null. It doesn't know anything. That is what it has been given. So distance vector table initialization and distance at the time of initialization, and even when it was a new table, it is the distance to itself is all it is 0. Okay, so it does not the distance to all other nodes is also been is initialized to 0. Okay, it does not know because only by sharing and getting the information only it can able to know. Okay, so what actually this distance vector routing algorithm is going to do? That is what distance vector routing algorithm, what it is going to perform. It's a router, it transmits its distance vector, that is its distance vector table to each of its neighbor in the routing table. So as I said, it is going to share the routing table to each neighbor in the routing packet. And each router, what it is going to do in the sense, it receives and saves the most recently received distance vector from each of its neighbor. So as I said, each and every node that receives the information of its neighbor, it is going to update, and that updation is also going to be done only the recent change that has been made, but not the old change. Old change is left as it is. If there is a recent change in the table, that is will be updated in the distance vector. Okay, so that is what they are saying. And at the same time, the router recalculates its distance vector when. So here, as I said, how does it going to update this routing table? At what time it going to update the routing table? When it is going to recalculate this distance vector? At what stage? So number one, it talks about it receives a distance vector from a neighbor containing different information than before. Okay, if suppose there is a new change, a new address has been there, or new node has been there in the neighbor table in the sense, then that will be updated. So that is something about the first point it talks about. It receives a distance vector from a neighbor, you would have a new information or different information than before. Another one says it discovers that a link to the neighbor has gone down. If there is any link to the destination or to the nearby node has been gone down, or it has been failed, or it has been dropped, or it has been closed, anything in the sense, then there is a topology change. And at that time, there is a need for updating the routing table. That is recalculating the distance vector, and that is to be updated in the routing table. This is something about the distance vector routing algorithm does. The distance vector actually each and every time what it is going to do in the sense, it performs this calculation, and that is based upon the minimum cost to each and every destination. So here the updation of the routing table is only on calculation as per the nearby routing table, with based upon the least cost it has. Okay, so the least cost, the minimum distance, the minimum cost in order to reach the respective nearby node. That is only will be selected. The distance vector routing algorithm, in short, what they say is, so each and every node has its table, and that table has to be updated each and every time by sharing its knowledge with the nearby neighbor. And if there is any new information, that will be updated, or any change in the topology, that will be updated in the distance vector routing table, so that the distance vector routing table has only the minimum route in order to reach its near destination node in the particular topology. That is something about the distance vector routing algorithm. I hope you are listening to it. Okay, so this is the three keys to understand. So based on the idea what I said, what is this distance vector? The three key ideas in distance vector routing algorithms. Distance vector routing algorithm first it has to know about the knowledge about the whole network, because when only it knows the knowledge about the whole network, it can able to do sharing and updating of this routing table, right? So it has to know the knowledge about the entire network, as well as it has to route only to its neighbors. So it has to share the information only to the nearby neighbors, but not more than that. That is not possible. Okay, it only hop to the nearby table. So routing only to the nearby neighbors and information sharing at regular intervals. So these are the three important key points in the distance vector routing algorithm. Okay, so the three key points are the knowledge of, it has to know the knowledge about the whole network. It has to route only to its neighbors. At the same time, it has to do the information sharing has to be done at regular intervals. So these are the three key points in the distance vector routing algorithm. Okay, so next talking about the first, let me talk about the knowledge about the whole network. So what is this knowledge about the whole network? So here each and every router has to share its knowledge about the entire network. Okay, each and every router. So whatever it knows, whatever it is not that the router have to know the knowledge about the entire. So whatever the knowledge know, if it has, if it knows the knowledge about the nearby node, it will update. It will have that information. If it does not have, then that will be considered as infinite, whatever it is. Okay, so here each and every router, what are the information it knows about the network, that is updated, and that will be shared among its neighbors. Okay, that will be shared. That is then that in by sharing only it can able to know the knowledge about the entire network. Okay, the router sends it's collected the knowledge about it. That is how only possible it knows the knowledge. Otherwise, it's not possible. Only by sharing of its table only it come to know that these are some of the nodes we have in this particular network, and what is the shortest path to not reach that particular network. And that idea is only by sharing only happens. Then routing only to neighbors. So each and every node is distributed only to its direct neighbors, but not more than that. So it can communicate directly with only its nearby neighbors. The router sends its knowledge about the network only to the nearby neighbors with a direct link. Okay? The router sends whatever it knows about the network, whatever it knows. It is not going to hide something or not like that. It knows, it will send information, whatever it knows about the network, whether the link is there or whether it's not the link, whatever it get from the neighbor, whatever it knows about it, it will be updated and it will be shared. Okay? Then the information received by the router uses in the information update its routing table. So whatever the information it receives, if it is new to it, it will update. Otherwise, if it is old, it will keep as it is. It will not update. If it is new in the sense, it will cross verify and it will update that into the routing table. And that sharing of information have to be done regularly. It can be within of each and every 30 minutes or each and every 1 minute at regular intervals. That particular knowledge of routing table will be shared and it will be updated by each and every router. This is the main important three key points of the distance vector routing algorithm. So sharing of information, the first one is about only, so how it knows the knowledge about the entire information only by sharing. Okay, as I said. So here each and every, this is a sample network that is being drawn. Okay, so in this figure, each and every cloud. So here this cloud Okay, we have net 1, a child network ID 1, network ID 2, network ID 3. That represents the each cloud represents the network, that is a network, and the number itself, the cloud represents the network ID. So here this is for A and B link, it connected with the help of a network ID 1, and B and C is get connected with the network ID 4, and A and F is get connected with the network ID of 2, and A and D is connected with the network ID of 3. Okay, so this is how E is connected with the network ID of 3, and then E and D is connected with the network ID of 8. Okay, this is how what the network ID. So how each and every A and B or C are get connected, and it is been given. The distance vector routing. So in this figure, each and every all the LANs are connected by routers. So each every LAN network, that is a network. So we are if it is a network in the sense, then it is get connected to a router. So each and every LAN are connected to a router, and they are represented in the form of boxes. So this A and B, C, all these colored boxes like that is labeled by A, B, C, D, E, F, G. All these role is represented the routers. They are the role of routers. This network ID cloud is the network, and these are the routers. The distance vector routing algorithm simplifies the routing process. Okay, by assuming the cost of every link is 1 unit here, so it just simplifies the routing. So here this algorithm this network ID algorithm. I mean this diagram, it represents that this is a simplified representation of how dynamic vector routing algorithm works by thinking that the cost between the two network is only of 1. Okay, that is what they're saying. This is routing algorithm simplifies routing process by assuming the cost of every link is only 1 unit. The cost of every link is, that's because when I connect A to network ID 1, then if the cost is only 1. If that network ID is get connected with the B, then the cost is 1, and B to network ID 4, then the cost is 1, as well as network ID 4 when it is connected with network ID, I mean, if the router sees that the cost is only 1. That is what they're saying. So each and every link has 1 unit, and therefore the efficiency of the transmission can be measured easily, and the number of links to reach the destination. So if A wants to reach the see how many links it needs, like 1, 2, 3, 4. So totally it needs 4 links with the cost of 4. Okay, so that is something about talks about the routing link and the routing the cost. The metric that is being chosen is the cost between the node source node A as well as the destination node C. Okay, this is the distance vector routing table. It is based on the one hop count. Okay, the count is based on one hop count. So this is something about the sharing of information. Next is the distance vector routing algorithm. So what is that? So by sharing of the information, it comes to know the entire topology of the information. So in this figure, we observe that so the router sends the knowledge to the intermediate node. So it sends information about its own routing table to all the intermediate node, route neighbors, and that neighbors add this knowledge and will send this information, updated information to the nearby neighbors once again. Okay, so in this, so that is what they are saying here. So this A has its own information, B has its own information, C has its own information, and that will be exchanged, and that exchange information will be updated, and the updated information again it will be shared. So this is happens periodically. Okay, so in this figure, we observe that router sends the knowledge to the immediate neighbors, and the neighbors add this knowledge to their own knowledge and sends the updated table to the own neighbors. Once again, it is updated, and the updated information again it will be shared. This will periodically it will happen. That is why we said one of the characteristics of distance rate routing algorithm is iterative. It will happen iteratively until it will get the knowledge about the entire topology. Again, if there is any change in the topology, again that is this iteration happens continuously. Okay, so in this way, the router gets its own information, and the new information about the routers will be shared and updated. Okay. This is something. Next, how to create the routing table, the distance vector routing table. So how we have to create this is partially by in the example we can see later. So basically, let me study about how to create this. That is important concept in distance vector routing table, because the routing algorithm, it plays a vital role in updating of the routing table. Okay, so for that, first we have to create the table, and then we have to update the routing table periodically. This creation and updation will happen. How it will happen. So that is what we are going to study in the next few slides. So it talks about how we have to create the table and how we have to update the table periodically. Okay. So creating the table. So what do we do in creating the table in the sense? Initially, So the routing table is created for each and every router. Router has its own routing table, and that will make it have each and every routing in the distance vector routing algorithm. There has three information. One is the network ID and the cost. It has to know about its neighbors and the number of hop it needs to not reach the destination. Okay, it has the cost as well as the hops, number of hops. Okay, so these are the three information it has to know: the network ID, the cost, and the next hop. Network ID, it defines the final destination of the packet, that is to which particular network ID it has to reach, whether network ID 1 or network ID 4 or network ID 7 or whatever it is. So it have the ID of the final destination. Another one is the cost. The cost here, it represents the number of hops it needs in order to reach the destination. How many number of hops it has to not need? For example, if A wants to, in this diagram, in the previous diagram we saw, for example, A wants to reach B in 2 hops in the sense, that will be updated there. So this is from A to network ID 1 and network ID to B is, that's another one. So we need 2 hops, right? So that will be updated in the routing table. That is the cost. Okay, network ID and the cost it needs not reach a particular network ID. And next hop, who is next nearest neighbor? So that will be updated in the next hop. Who is the next nearest neighbor? That is the router to which the packet must be delivered. So the nearest neighbor where the packet has to be delivered. Okay, so that is something about the next hop. So this is the how we have going to so creating the table. So initially, when a new node is being installed in a particular network, initiated in a particular network, or it has been joined in a particular network, that particular network has to create the table, and the table links, the contents of the table, it will be blank because there will be no idea. So it is only blank. Only by sharing and updating only it will tries to fill the particular table. So initially it is nil. Okay. So that is the procedure for creating the table. So next, so here see how it is the table is created in this figure. The original routing tables are shown of all the routers. This is the original routing table. So for example, if you take A, so it for reaching the network ID 1 and network ID 2 and network ID 3, so the known information in the sense not reach the network ID 1. Okay, so first is the network ID and the second one is the as we said. So here see the first one is the network ID, next is the cost it needs, and the next is the next hop it has to go on. Okay, these are the three important parameters we need for the creating the table. So here, when we talk about how it has been created, the table, because the nodes are initiated in a network, and each and every node has its own routing table based on the basic information it have. What does it know in the sense? For example, if you take A, it knows that network ID 1, and for not reach the network ID 1 is it needs only one hop. That is 1. That is why it is represented as 1. For example, if it needs to go to network A wants to go to network ID 2, then it has to go only one hop. That is why it is given as 1. And if A wants to go to network ID 3, it has to go to only one hop. So that is why it is updated as 1, 1, 1, all those things. For example, with the B, so B have only 2 entries. Why B have only 2 entries? In the sense, only B have only 2 outputs. There is only 2 output links that is connected to B. One output is connected to network ID 1 and another output is connected to network ID 2. So please carefully look onto the directional link in the link that has been linked in each and every network ID as well as the routers, the colored routers. Okay. So we have only 2 entry in its distance with routing table. And what is the 2 entry in the sense? One is with the network ID 1 and the one is the network ID 4. Okay. It can reach both at only one single. Whereas if you take C, C also have only 2. Okay, one is with the network ID 4, another one is network ID 7, and again it have only one hub. The same. This is the basic information each and every node have. Okay, the basic information about the how to create the table. Okay, next we are going for updating the table. This is the important part here, updating the table. Okay, so how what we have to do for updating the table. So what is the major role in updating the table? You see, I'm talking about updating the table is here. When A, for example, if a node, when A receives a routing table from B, so when talk about A, so assume that A is receiving a routing table of B. Okay, then it uses its information to update the table. So what information does A will use? In a sense, it will use the B's information for updating the table. Okay. So for example, I'm talking about A is getting the information from B. So A is going to update the table by knowing the information of B. What B knows, that information will be known to A. Because A knows how to reach network ID 1, network ID and 2 and network ID 3. But B knows how to reach network ID 4. That is a new entry, right? Okay, that new entry has to be updated in A. Okay, so that is what we are going to see, updation. How A is updating that information into its own routing table. Because since I said A knows only the 3 network ID, but A does not know what is the network ID 4 is doing, and but B knows what network ID 4 is doing, and that is shared with A, and A will update that information about the network ID 4. Okay, so that is what is called as updating the table. Okay, that is what we are going to see now. So like I'm assuming that A is receiving a routing table from B, then it uses the information to update the table. So it uses the information of the B in order to update this routing table. So what is it information it have for each? What is it in that in the sense? So as we all know, this is a B table. Okay, B table for network not to reach network ID 1, it have gone to only one hop. For network ID 4, it needs only one hop for network ID 4. Okay, so this is the basic information of the B. So once this information received by A, okay, so with because it have only one hop, because it not reach B, it has only one hop. What it will do in the sense, the B is a neighbor to A router. The packet from A to B can reach its one hop. It has reached by only one hop. So one is added to all the cost because it is only one hop, right? So one is added to all the B's table, the given in the B's table, and that sum will be updated in the table. Okay, that is after adjustment. So how it is adjusting, because B A it gets the information of B to A, okay, and B to A is one hop, and that one hop will be updated in the A's table. Because how it happens? See, for example, so according to B, okay, so see, please check to it. Now it was before it was 1 1, and now not according to B. Network in order to reach network ID 1 is only one hop, right? Now B is sending that information to A. So B to A is one hop. That one hop is updated here. Okay, that is why it is being given as 1. 1 plus 1 is 2. And who is the next neighbor is 31. It is getting information from B. So the next hop of A is B. So B is in the third column. Okay, the same thing is happening here. Okay, next second column. What is the second one? According to B, network ID 4, not least network ID 4, it is only one hop according to B. Now A is getting that information from B. So A is going to be updated. So what A is going to do in the sense, okay, it knows the information about network ID 4, and according to A to B is one hop, and again B to that network ID 4 is another one hop it needs. So it is updated as 2, and that is reached only with the help of B. So this is a new entry actually. Okay, now after adjusting the A, then A what after making this adjustment, what A will do in the sense, A then combines this table with its own table. After making the updation, A will combine this updated table, this small table, to its own table, not to create a combined table. So this is the own table. Okay, in this table we know that network ID 1 is 1, and network ID, not its network ID 1 is 1, and network ID 2 is 1, and network ID 3 is 1. Now the updated has been given as, with the help of B, if A wants to reach network ID 1 is, the cost is 2. Now it is going to check which is the minimum cost. So A not reach network ID 1, the cost is only 1. But with the help of B, if it wants to go to network ID 1, the cost is 2. So 2 is highest, right? So it will keep the old entry. It will not update the new entry. So that is why it is given as the first column, first row, it is defined as 1 1 dash. Why? Because it is comparing, and by comparing it found that the cost is high. A is through B, if it wants to reach the network ID, the cost is high, and that is why that particular link is cancelled, and A uses its old entry. Okay. Now next is 2 1. According to A, when network ID 2, when A wants to add, can join network ID 2 with the help of only one hop. Okay, but that is not there. That network ID 2 is not there in B. So it is left out as it is. Okay, 1, 2, B, it is left out as it is. Okay, next 3, 1 dash network ID 3. So what does it here is 3, 1 dash. So upon node A, if it wants to reach network ID 3, the cost is only 1. Okay, but since that is not there in B, on reaching the network ID 3, it is also left out as it is 3, 1 dash. But the fourth one, it is a new entry, right? Okay, so that new entry is again it is updated in the table. So this is our table. So here just combining, it's just combined and write. First 1, 1B, then 1, 2B, then 1, 2, 1B. It's just combining and writing it out. So now the checking and comparing only will be done later. So checking and comparing in the sense for each and everything, it has to mention the cost is set. The network ID 1, if it wants to reach the network ID 1, the cost is 1. But if A wants to reach the network ID 1 with the help of B, the cost is 2. So which one is the minimum is 1 or minimum, or whether 2 is minimum? Of course, we all know that 1 is the minimum than 2. So it uses the old entry. So for that case, this comparison will happens in the next phase. Okay, this next phase, this combined table and the new table will be updated by doing this comparison, and the node will have the least root will be selected, and that will be used here. Okay, so that is something about the in distance vector routing. That is the new table of the A's new table. The combined table may contain some duplicate data. So what it have to do in this one, the combined table of the router A contains duplicate. So it keeps only those data which have the lower cost. The data that have the minimum cost only will be updated. The older one will be rejected. So for example, A can send the data to network 1 in 2 ways. The first way, it uses no next router. So it directly have only one hop. Whereas in the second case, it can reach the network ID 1 with the help of B. Then it have 2. So only the best one will be chosen. Okay. So this is the procedure of distance vector routing algorithm. So what it is actually does, it needs to share the table, and it has to create the table and update based on sharing of information, and that update also will be shared, and this sharing and updating will be done each and periodically of time. This is something about the distance vector routing algorithm. Okay, so now this is the final route, okay, for this particular table. Okay, initially it was like that, right? After sharing and updating of the information, and finally each and every node will comes to know about the entire information about the topology, and that will be updated here. Okay, so that is something about the distance vector routing algorithm. In depth, we are going to see in depth actually. So what actually, how it works. So this distance vector routing algorithm, it works, the finding the least cost and updating that will be done with the help of an algorithm, what is or the algorithm, or with the help of an equation that is related to it is something what is called as Bellman-Ford equation. As I said before, distance vector routing algorithm, also called as Bellman-Ford algorithm. Why? Because in order to find the minimum cost and updating of that minimum cost, it uses a special equation, something what is called as the Bellman-Ford equation. Okay, this is the special equation. This is the equation. Okay, Bellman-Ford equation. So dy of x is nothing but the minimum of it is a c to the x comma v plus direct d of v of x. So what does this? In detail, when you talk about this particular equation, is d this where is this minimum of v is the equation taken for all x neighbors. So, for example, if you take on let dx of y, this dx of y is the cost of the least cost path from node x to node y. So if your source node is x and the destination node is y, so we are going to send a packet from node x to node y. Okay, so I want to know the distance between the node x and node y. So for that I have to calculate, and the minimum route path will be selected, and that will be assigned as a cost path. Okay, so that is what we are saying. The distance d represents the distance. The distance of between the node x and y is nothing but the costs that have the least cost path from the node x to node y. That least cost is only selected with something what is called as the Bellman-Ford equation. So distance of x and y is nothing but the minimum, the least cost, but not the minimum of the cost. Okay, that is why they are saying minimum of the cost of x to the v is nothing but all the intermediate vertices or the intermediate nodes between the source node x and the destination node y. Okay. So after traveling from x to v, if we consider the least cost path from v to y, then the path cost will be from c of x comma v2. So it will goes on from x to v, v to x, v to e, c, or it goes on until it reaches the destination. So this is how the minimum cost path will be selected. Okay. So this is the equation of Bellman-Ford. Okay, cost of least minus cost path from x to y. Okay, so this is the definition of the Bellman-Ford equation, and we have the formula this is the formula d of x to the y is nothing but the minimum of c of x comma v plus dv. V is nothing but all the intermediate nodes, the vertices of all the intermediate nodes. The c represents the cost of the particular two node, and the d represents the distance between the two node. And among this, which one has the minimum, that will be selected and updated and used as the minimum route path between the source and the destination. Okay, so let me see this equation, explanation of this equation in detail with an example. Okay, when we know the explanation on the example, by means of an example only, we can able to clearly know how it actually works here. Okay, so the Bellman-Ford example. Okay, so here this is a scenario is being given, a scenario of a Bellman, for example. So this is the root cause, because please be careful and listen to it, because why? Because the gate exams, what we're going to next is something that here see the topology will be given, and based on the topology the questions will be given, and how we are going to solve the questions, solve each and everything, every questions that is to be solved only on based on this the Bellman-Ford equation algorithm. Okay, so based on when we know that Bellman-Ford equation, we can able to solve these particular, see each and everywhere the algorithm, the graph will be given, and you have to work it out this particular graph based on that Bellman-Ford equation, and have to find the least cost path route. That is something about that talks the distance vector routing algorithm. In distance vector routing algorithm, Bellman-Ford plays a vital role, and based on that particular equation only, we can able to find the least cost path, and that will help you to find the least cost path route. And that is of course the question for each and every gate sampling. Most probably in all gate questions in distance vector, we have to know how to find the least cost path. If we know this least cost path, then it will be very easy to answer any question, the gate question in related to this particular topic. So that is why I am very much clear about to say that. So please listen to this how it works. This Bellman-Ford example. Please listen to how it works. Okay. So here, so it has been defined, and it has been clearly said that this is a equation. This is assume that this is a sample network topology. Okay, we have some totally of about 3, 4, 5, 6 vertices. Okay, 6 nodes. U, V, X, W, Y is it. Totally we have about 6 nodes. Okay, so the distance between U to V is 2, and V to 3 is V to W is 3, and W to Z is 5. And the same of U to X is 1, and X to W is 3, and X to Y is 1, and W to Y is 1, and whereas W to Z is 5, whereas Y to Z is 2. This is a part has been clearly defined. Okay, and of course, if you want to reach W, the cost is 5. Okay, it is all given. So now the distance between V to Z. Please make sure, be clear, the distance between V to Z is given. The distance between V to Z in the sense from V to Z is 5. Please listen, V to Z is 5. How we know that the distance between V to Z is 5? Already it is V to Z is from V to W it is 3. Okay, then W to Z is 5. So 5 plus 3 is 8 actually. But they are saying that distance of V to Z is 5. So that is the calculation we are going to find it out. In simple to say that There is only one path to reach Z? No, we have another path. Another path is we can also reach Z from V to Z. I can also reach from V to Z. There's also another path. I can travel from V to X and X to W and from W to Z. From V to X, the cost is 2 and X to W is cost is 3. So 3 plus 2 is 5 and W to Z is cost is 5. So 5 plus 5 is 10. Oh, it is higher than the previous link. That is from V to W, W to Z, the cost is only 8. Whereas from V to X and X to W and W to Z, the cost is 10. No, this particular route, it will not suit. Okay, we, according to the distance vector routing algorithm, we want the minimum route, not the highest route, the highest path route, right? So now there is also another route. What is that? I can also reach Z through another path, that is V to X, X to Y, and Y to Z. From V to X, the cost is 2, whereas from X to Y, the cost is 1. So 2 plus 1 is 3, whereas the cost of Y to Z is 2. Then 3 plus 2 is 5. Among the three paths, which one is the minimum? Then 5 is the minimum. So that is how the selection happens. Okay, that is, it is being clearly defined. So that is why they are saying that from the distance of V to Z is 5. The same from the distance of X to Z is 3. The same of the distance from W to Z. W to Z is 3. Okay, because W to Z direct link is uh, Y to Z. Okay, this is something about the Bellman 4 example. Okay, so yes, see. Let me see with the equation. Bellman-Ford equation says that now we are going to find, okay, the cost of the distance between U to Z. I'm going to find the route from U. Your source is U, the source is U, and the destination is Z. Okay, source is U, and the destination is Z. And we are going to travel here from U to Z. What is this cost path? We are going to find the cost. Okay, so now distance between U to Z. So for that we are going to find it out by means of the Bellman 4 example. So we have to find the minimum of the cost. So what is the formula? We have to know the cost of U. First they have to know the cost from U to V and then distance of V to Z, because I already know the distance of V to Z. Okay, then I have to know the cost of U to X and the distance from X to Z and the cost of U to W. Okay, so U to W and the distance of W to Z. So what is this? So by calculation we know that cost of U to V, cost of U to V is 2 plus, okay, cost of U to V is 2, 2 plus distance of V to Z. We all know distance of V to Z is 5. So 2 plus 5. So 2 plus 5 is, what are they saying? So from traveling from U to V, V to X and X to Y and Y to Z is, the cost is 2 plus 5 is 7. Okay, next. Using, if I'm going to choose what is this V, the cost is 7, whereas I'm going to put another cost, another link, that is what is the cost of U to X and from X to Z. So X to Z is X to Y and Y to Z. That is the minimum cost, right? We all know that because X to Z, the cost is, what they are saying is 3. Okay, the cost of U to X is 1. So 1 plus 3. So we have totally, with the minimum cost is 4. We have only cost is 4. Previously the cost was 7 and now the cost is only 4. So this is another path. The previous path it was 7 and now this path we have the cost of 4. And the third path, we are choosing the third path, that is U to W and W to Z, distance of W to Z. The cost of U to W is, 5. It is already mentioned there. The cost of U to W is 5. 5 plus and the distance of W2Z, we all know it has been clearly given. W2, distance of W2Z is 3. So 5 plus 3 is 8. So we have totally 3 paths. The first path is bit from U to V, V to X, X to Y, and Y to Z. The cost is 7. Whereas we have another path from U to X, X to Y, and Y to Z. The cost is only 4. And we have another path that is U to W and W2, Y and Y2 is it, and the cost is again it is 8. Okay, so from this the minimum cost is nothing but when from the source U to Z, the minimum cost is going through the root of X, U to X, X to Y, and Y to Z. So this is the minimum cost. So finally it been concluded that the minimum cost distance of U to Z is only 4. Okay, this is how the Bellman-Ford example. We've seen this Bellman-Ford example. The route is being, the least cost route is being find it out, and the best route is being selected, and the data packet is being transmitted from source to destination. So this is how it happens. Okay, so this is the main role of the distance vector routing algorithm. Okay. So here see, and the simple scenario, a simple of x, y, z, okay, x to y, and I hope you all understand. You have coming up along with me. I hope you all know about it. Okay, you're coming up with me, right? All the boys and girls, those who are here. So why we have totally of about 3 nodes here. Please be careful here. We have 3 nodes: y to z and x to y and y to z, and the path is being cost is being defined. So now, how, using this distance vector routing algorithm and Bellman-Ford example, we are going to update each the table of x, the table of y, and the table of z. So what is the node x table, and what is the cost from x to x, x to y, and x to z. Initially it was 0 because initially it does not know only from, and this is the initial table of x. Here this is the initial table of x, this is the initial table of y, and this is the initial table of z. Initially the table is being given. Okay, and that is the initial table. And for example, if you take the initial table of x, is that from x to x it is 0. So x2, when I am reaching from x to x, it is 0, and x to y, so when the x reaches to y, it knows only it is 2. Okay, when x wants to reach z, it is only 7. So remaining, and if the all it is infinite because it doesn't know. This is a table of x because remaining y and z it does not know. It is infinite. Okay. Next, node of y. What according to y, y wants to reach x is 2. If y wants to reach y, it is 0, and y wants to reach z, it is 1. Okay. That is it is the initial table of y, and of course this is the initial table of z. When sharing happens, when y senses information and z senses information to x, then processing this using the Bellman equation, the processing will happens and the minimum will be chosen. For example, d of x of y. Okay, d of x of y. So when y is sharing this information to the x, okay, y wants to send information to x. So what does it do in the sense? So here it is going to find out the minimum cost. Okay. So for that we have to go on with the Bellman equation of to find the cost of x comma y, then the distance of y to y, and the cost of x to z, and the distance of z to y. So from this equation, from this diagram, it is clearly known that the cost of because initially know that the cost of x to y it is 2. We all know x to y it is 2, and the distance of y to y is 0, comma, and the cost of x to z is 7, and the distance of z to y is 1. From this we all know that, so 7 plus 1 is 8. So which is the minimum? This is 2 and this is 7. So choosing this is the best. The 2 is the best. Minimum of 2 comma 7, minimum is 2. So which one we have to choose? In the sense we have to choose the cost of x comma y plus distance of y to y. So that is updated here. Okay, so that is what. So y to x, the 2, it is updated as x to y. So x to y updated as 2. Okay, that 2 is updated here. Here see 2 and 2x to y, the 2 is updated here, as well as x to z. How the 3 is updated? If previously it was 7, and now after sharing of information, now it is found that the distance is 3. Okay, so by going on with this, if we find solve this particular problem, we found that the minimum of 2 plus 1 is 3 and the 7 plus 0 is 7 and minimum of 3 comma 7 is 3. So it is best. So distance of x to z, we found that the minimum is 3. So the 3 is updated. So each and every entry, by sharing of information, it is updated and it has been delivered. Okay, so this will give you the clear information how each and every entry is updated and it has been given. And finally, this is the entire topology. The table of the entire topology table has been given here. Okay, so after a short period of time, the each and every node updated, and that entire information will be stored and it in this way. Okay. This is the algorithm, distance vector routing algorithm. Okay, for all destination of y and y, the distance of x to y is nothing but the cost of x to y. So if y is not a neighbor, then if it is considered to be as infinite. And for each neighbor of w, we know that d of w is 1. So for all destination of y, 10. For that, that is what we are going to find out for each neighbor. So we have to send the distance vector of distance between the two of node, and this because this is a sharing will take place. The loop continues, the sharing will take place, and wait until I receive any distance vector from some neighbor. So the sharing of information will take place, and it will wait until if anyone shares a table, then processing will happen. So which one is the minimum cost? The processing will happen, and this until the updation of table, this will goes on. This looping will be goes on forever until we get the entire information of the particular topology. Or okay, so this is something about the table. Now let me see some of the gate sample questions we have in this topic. Okay, these are the gate sample questions. So the question will be given, the topology will be given, and some this is the biggest question. Some descriptions will be given about this topology, and we have to find it out by solving based on this Bellman-Ford equation algorithm. If you are very clear enough, and we can easily it is being solved. It is all every simple question is if you know the concept clearly. Okay, so let's see. So this is a topology of how many nodes in the sense: node 1, node 2, node 3, node 4, node 5. Totally we have about 5 nodes. The cost of node 1 to node 2 is 1, and the cost of node 2 to node 3 is 6, and the cost of node 3 to node 4 it is 2, and the node 4 to node 5 it is 4, and node 5 to node 2 is 3. So the cost is being given in detail. Okay, that has been okay. And the distance vector of different nodes. Okay, the distance vector of different nodes also been given as the node 1 is 0. If node 1 wants to reach node 2, node 1 to node 1 is 0. If node 1 wants to reach node 2 is 1, and node 1 wants to reach node 3, it is 7, because 6 plus 1 is 7, and node 1 wants to reach node 4, it is 8, because 6 plus 1 7, and 8, and if it wants to reach node 4, node 5, it is 1 3 plus 1 is 4, it is 4. Okay, so each and every the reaching of each and every node 1 to another, all the other nodes has been given. The link path has been given. Now what happened distance vector? Each distance vector is the distance of the best node path. Okay, we all know that from n1 to n5, that the distance to itself is 0. Okay, also all links are symmetric. Okay, the links are symmetric here, and the cost is identical in both directions. So cost is same in both directions. In each round, what happened in this sense, all nodes exchange their distance vector. So for each and every round, every single node, because node 1 will share this information node 2, and node 2 to node 3, and node 3 to node 2, and node 2 to node 5, something like that. Okay, so for each and every round, all nodes exchange their distance vectors with their respective neighbors. Then all nodes update their distance vectors. Okay, in between two rounds, okay, what happened in this is any change in cost of a link will cause the two incident nodes to change only that entry in that distance vector. So what happened in the sense, here each and every time what happens in on one of the round, okay, so there is a change in the cost of the links that cause two incident nodes to change. Okay, there is some change in the particular ring. So after the next round to update, what will be the after the next round of update? Okay, there is a change in two cost. Okay, after the next round of update, what will be the new distance vector at node 3? So what they are asking, what will be the after the change in the cost, what is the distance vector at node 3, whether it is 32025 or 32026 or 72025 or 72006. So here the answer is given as A. So how the answer is given as A? So because we have to calculate the Bellman-Ford equation, because they are clearly saying that the cost has been changed in on time. Okay, so what is the choice? What is the distance vector of node 3? Because node 3, it was like before, it was a 76026, 76026, but now it has been changed to something like 32025, or did it is changed to 32026, or did it change to 72025, or did it change to 72026? Which one is the best choice? Which one is the correct choice? We have to choose. Okay, so so for that, we have to, the solution has been given. Okay, so from this solutions, we have to update the table. So the updation of the table has to be done for each and every round. Okay, so an updation of the and then n3 will receive something like 10273 after the first update, and from n2, and that will be updated, and to distance n1, and as well as n5, as 3 and 5 will be updated. So because first, well, because the change of root, right? So first n3 will receive something like 10273, and of course n3 will update to n2, and from and n2 will receive it will get information from n2, as well as it will get information from n5, because of the change of two roots. Okay, and because n2 also will be updated, as well as n5 also will be updated, that information also will receive by the n3. So based on the information from n2 and n5, so it has been the change that the non node link will be changed as 320, because 3 and 2 is 5 are the respective change that happens. So it is changed as 320 to 5. Okay, so this is the answer A, example question. So A is the correct answer, because we have to calculate the Bellman-Ford equation have to be applied here. Okay. Next simple question. So the same, based on the previous question, and the question follows here. After updating the previous question, the node link N1 and N2 goes down. Okay, link N1 bit N goes down. So N2 will reflect this change immediately, as cost is infinite. After the next round of update, that will be the cost of to N1 also in the distance vector of N3. What will be the cost to N1 in the distance vector of N3? So N3, according to N3, what is the cost of N1? So that is what they are asking here. So answer is 10. How in this, in the next round, because n3 will receive distance from n2 to n1 as infinite. N3 will receive distance from n2 to n1, because the link between n1 and n2 is failed. But it will also receive the same distance from n4 to n1 as 8, because n1 have, it still is linked with n1, right? So it will have the distance as n4 to n1 as 8, so that it will be updated to distance to n1, because it comes to know, because it does not know, because it knows that there's no way through n2. N3 does not know that it does no way to using n2 to reach n1, but it can reach n1 with the help of n4. So the that node will be updated. That root will be updated as 8 plus 2, and that is something what is called as 10. So that is the answer for this. Okay. And again, there is another diagram is given. And again, we have to. So what is the consider network with the 6 routers? Totally, there are about 6 routers with all the cost has been given and the way it's been assigned. So all the routers uses the distance weight routing based algorithm to update routing table. Now each router, so each and every router starts with this routing table initialized to contain an entry of each neighbor with the weight of the respective connecting link. So each it will start like R1 have a weight with R6, and R1 has a weight of 3 with R3, and R1 has a weight of R4 like 60 plus 7 as 13. So like that, each and everyone have a own weight. After all the routing tables stabilize, after the routing table has been stabilized, is how many links in the network will never be used for carrying any data. Okay, so here once it has been stabilized, so what are the null? What are the null links? The default or the unused links. That is what we are going to see. The answer, what they are asking here is, so once this is been up stabilized and it has been initiated and it has been updated, there will be some link which is of not use. So how many number of links? They're asking a question of how many number of links will not carry any data. So whether it is 4 or 3 or 2 or 1, and the answer is C. So how the answer C, how it comes here, the solution is given. So here, for we can check one by one. So for shortest distance, we'll be checking from start writing from R1 to R2, R3 to R4, R1 to R5. So if I write down, we are just checking. So then this is the link of R1 and R2 and R3. See, it goes on decreasing finally, and from that it founds that the two links, this nothing but the R4 R6 is nil. So that is from that we can R1 R4 is there and R4 to R6 is there, but the two links are nil. So from this we can conclude that two links have been unused. Okay, links, the number of links used. Now to find the shortest distance from R1 to R2, what are the links? How many number of links are needed? And again, after defining how many links are there, so from this we come to know that two links are unused. Okay, this is a gate sample 4, and again there is another diagram has been given. Suppose the weight of all unused links in the previous question are changed to 2. So okay, the previous the unused link, that is the between the two that has been changed. There is a R5 R6. The change has been 2. Then what happened? What happened? Okay, what is this answer? So from this, how many links will now remain unused? From this, what is the answer here? Is again the answer is one again. So following will be the distance variable. So see for example for root 1, it is 2 and 3. No, for R1 to R2 is 2, R1 to R3 is 3, and R1 to 4 it is 9, and 5 is 10, and 6 is 11. Okay. So number of links used is R1 to R2, R1 to R3, R3 to R4. Okay, good. Then for the R2, how many number of links are used in this is? We used only 3 links. Okay, 2. So R1, R2 to R1 is 2, R2 to R4 is 7, R2 to 8, and R2 to R6 is 9. That's it. Okay. Next, again for R3, it is only 9 links used are, these are the number of links, and R4 is 1, 2. So what are the links used are? Only 3 links are used: R1, R2, R3, and R4. R4, R5. So from this we comes to R5, R4, R5, R6. R4, R5, and R4 to R5 and R4 to R6 are used, whereas R5 of 3 is found to be of not used. So there's only one link is being not used. Okay, remaining links. So how many number of links are used for between R4 to 1 and 2 and R4 to 3? So from by calculating each and everything, so it is found that the last link, that is the sorry that is the R5 to R6. This is the link that is found to be not used. Okay, since it of higher cost, it's been not used, and that is how what is question they are asking here. Okay, and again there's another question. What is the count to infinity is a problem associated with whether it's a link state routing protocol or a distance vector routing protocol. So now, of course we all know that distance vector routing, because it has an infinite loop to be down, and if there is any congestion or anything happens, this loop infinitely will run. So the infinity problem is found in distance vector routing protocol, and that is quite the answer for this. Okay, the last one. Consider the following 3 statements. So here the statements has been given, and about something about the link state routing. We have to know about the link state and distance vector. If you know this, we can able to solve this. Okay, let me see. Consider the following 3 statements about link state routing protocol and distance vector routing protocol for a larger network with how many network? 500 network, and there are about 4,000 links are there. Okay, so from this what they are trying to find out is so the links, the what is the S1 and S2 and S3. They have given the statement as S1 statement is the computational overhead in link state protocol is higher than in distance vector protocol. Okay, so using this 500 network nodes and 4,000 links, what they are saying is the computation overhead is high in link state, but it is less than the distance vector protocol. At the same time, distance vector protocol avoids persistent routing loops. With the help of this horizon, it can avoid persistent routing loops, but not a link state protocol. Link state protocol does not have. And after now the state 3, what they're saying is after topology, if there is any change in topology, a link state protocol only will cover faster than the of the distance protocol. So among these 3 statements, which one is correct? Whether it's a statement of S1, S2, S3, whether S1, S2, and S3 are all true, or whether S1, S2 are all false, or S1 and 3 are true, whereas S3 is false. But so these are the 4 different options it is being given, and it is found that the answer D is correct. Okay, so what is this answer 3? The D is this S1, S3 is true, but S5 is false. And why the this is because this is a property of the link state routing protocol. Okay, so that is why it is being found that this is true, and these particular 2 statements are true, and this particular statement is false based on the properties of link state and as well as the distance vector routing protocol. And last question is uh, another question. Two popular routing algorithms, distance vector elixir output, the following are true. Again, we have some certain set of statements like S1 count to infinity is a problem with distance vector, not with the link state. And in link state, the shortest path problem algorithm is run only at nodes, whereas in distance vector, the shortest path algorithm is only run at only one node. Okay, whereas in NS, it will run only node, or in this distance vector, the shortest path algorithm will run only nodes. Or whether distance vector requires less number of network message than that of the link state routing protocols. Which of the statement is true? Okay, that is the following question: whether it's S1, S2, and S4, or S1 and 3, S2 and S3, or S1, or which one is correct? So again, it has been found that answer D is correct because the explanation S1 is true, and of course we have count infinity problem, and S2 is false because link state because in link state the shortest route algorithm is run at every node after each node has broadcast its neighbor information. So here what you're saying is run at only one node. No, it is not like that. Both in shortest path, both the link state routing algorithm and the distance weight routing algorithm, not to find the shortest because each and every node is sharing its own information, right? So that each and every node plays its vital role in finding the shortest path. Not that only node. So both statements are false. And S4 is true since link state algorithm, every node broadcasts its neighboring information to all nodes, but in this node, it's not like the sense routing information to all nodes. It will broadcast that, it will send the information table. So that is why DV requires lesser number of network message than that of the distance link state routing protocol. Therefore, the option D is abruptly correct in this particular question. So if you know the concept of distance vector and link state routing protocol, it is very quite easy to solve the case questions. If you are very clear with the problems, then it will be very easy to solve. Okay, I hope you all enjoy this particular class, and thank you all. Thank you for staying with me. Okay, so I hope we let me see in the next class. Okay, thank you. Bye bye.